All right, welcome back to Chemistry B, everyone. We are going to be continuing on today with states of matter in our chapter 10 discussion. And today we are going to be looking at phase diagrams and heating curves. So this is part 2 of our states of matter discussion. So you can follow along with the notes posted there in Google Classroom if you'd like, or just listen on your own. But I wanted to start by doing a quick review of where we left off. Remember, we left off looking at the triangle with all the different states and changes in states and the names of those processes. So I just wanted to start by giving you a quick review of that with freezing and melting, looking at the energy we talked about, kinetic energy, which is the energy of motion, which we measure that kinetic energy of motion by the temperature, as you can see here in bullet point number 2. Freezing point is the temperature at which particles are moving slow enough to lock into place and become solid. So they're vibrating, but they're not moving around like they were in the liquid state. So at this point, temperature-wise, we have both states of matter, and that's what we want to look at today with this heating curve idea, is these two states of matter that are existing at the same time as the solid is melting and we're going to the liquid state, and we've got some liquid there. So we'll have both states present. The other thing that we talked about in our previous lesson was sublimation and deposition on that triangle with the processes in changing states. Sublimation, we talked about, would be an example of dry ice, like dry ice changing directly from the solid chunk or mass that we have into a gas. So this conversion is called sublimation when it happens directly from the solid to the gas. And then the backward process of that, going from a gas to a solid, is called deposition. So I just wanted to remind you of these terms and these processes, and wanted to look at these graphs today. This is what your assignment's going to be focusing around today, is a graph similar to this. So you can see on the graph, this is the heating curve of water, right? So we've got both graphically and visually here on the screen. You can see across the top there of the graph, we've got the different states of matter represented with atoms, and you can kind of infer what the behavior of the atoms is there as far as kinetic energy or their energy of motion, and maybe also what the temperature is, right? So we're going to start off down here at the bottom of the graph, and we're looking at the solid state on this angled piece. And if you follow that up, you can see that that's a solid chunk. That's all one state of matter. And what's happening at this angled point on the graph is that the solid is warming. So it's climbing in temperature, but through that temperature climb, it's still a solid because we haven't got to the melting point yet for this particular substance. So when we do get to the melting point at 0 here for water, because we're on the Celsius scale, as we talked about in the previous lesson, we typically use the Celsius scale for temperature, and water melts or freezes at 0 degrees Celsius. That's that transitional point. So for the water at 0 degrees, it's flatlining, and that flatlining is due to the temperature or the heat being used to change state rather than change temperature. So heat is still being applied as it was with the solid warming and climbing, but now the heat is being used by that state of matter, that solid, to melt and loosen, so to speak, some of those intermolecular forces between water molecules. So we have both states of matter present on this flat line here. We have some solid, as you see in the center at the top there, and that solid block is giving way to some liquid around it. If this were in a beaker or a container of some sort, you'd have maybe an ice cube sitting in a little puddle of water around it. And as we continue to heat over time, right, because the bottom of the graph on the x-axis down here shows that heat is being added across this whole graph. So we're continuing to apply heat energy to it. And as we do apply heat energy to it, that graph is going to continue to climb because now it's all liquid. And the liquid goes from a cold liquid to a hot liquid. So we're warming the liquid up, and again, you can see that line is climbing in temperature up to the 100-degree mark on the Celsius scale here over on the y-axis. So as we hit the 100-degree mark, if you look in the next segment of the graph, you can see that you have gas and liquid present at the same time. So down at the bottom of that box at the top, you've got some liquid that's still moving around very closely, packed together, very dense. And then you've got some particles up above that that are scattered out, and that's your gas particles that have vaporized from the liquid. So again, at this flat line, we're still adding heat, but the heat is just being used to break those intermolecular forces now in the liquid water and set them free to float about freely as water vapor or as a gas. Okay, so if we could capture the gas, we could then continue to heat the gas, as the graph would indicate here, over on the far right end of the x-axis as heat is being applied. We could continue to heat that gas into superheated steam. Okay, and all of the matter that's present, the water that's present in that last little segment on the graph here, is showing you that it is now all in the gaseous state. Okay, so this is called a heating curve. Again, it's showing water for this particular heating curve. But just to summarize, the angled lines where the temperature is increasing, the matter is being heated or it's increasing in temperature. And then those flat line areas are where it's changing state. Okay, so flat lines represent a change in state, angled lines represent a change in heat energy, kinetic energy, or temperature. So next we want to move to a phase diagram. Okay, and there's a few things to know about phase diagrams. We have two phase diagrams in this particular graph on this slide. This phase diagram on the left-hand side is representing a phase diagram or change for water. The one on the right is representing carbon dioxide or dry ice. Okay, so if we look at these and just get an overview of what is in the graph is representing pressure and temperature. Okay, so pressure is being represented in ATM, which is atmospheres, is our unit of pressure. There's a number of other units which we'll talk about when we get into gas laws, but just note that the ATM is representing atmospheres of pressure, which is representing how much pressure in the atmosphere is pushing down on you. On the x-axis, going across the bottom of both of these phase diagrams, you have temperature in Celsius. Okay, so you have the little degree C symbol to represent the temperature in Celsius. So you can see it's kind of broken into quadrants for each of these phase diagrams. And these quadrants are representing different things as they're labeled here. In the water one on the left-hand side of your screen, you can see that ice is the green shaded area. It's on the far left of the graph, taking up most of that left-hand side of the graph. So we're in the solid state for water. If you are kind of in the middle or top and you move to the right on your screen there, you'll move into the liquid quadrant. And down at the bottom in the tannish orange colored area, you'll see that we have gas. Okay, so we've got all three states of matter represented on these phase diagrams, which are representing different phases of matter. Phases, remember, are our states solid, liquid, and gas. They're each represented on this graph. So what's happening or being represented by this graph is the substance is changing state. So for our graph on the left, we're working with water, and we can see that normal atmospheric pressure is 1 atm on the left, and there's a dotted line that goes across from 1 atm. It proceeds to the right on the x-axis, and you go through the solid state or ice in the green quadrant. You hit letter B, that dot, which is the interface there between the solid and the liquid. And then if you continue straight across that dotted line, moving to the right further, you'll go through the liquid state and hit dot letter A, which is our transition between liquid and gas for water. So notice the temperatures down on the bottom. If you take a look at the x-axis down there, the temperature for our solid to liquid transition in the green to blue quadrant is occurring at 0 degrees Celsius. In our transition from liquid to gas at dot letter A, you follow that down to our temperature in degrees Celsius on the x-axis again. You can see that it's 100 degrees. So kind of similar to the heating curve that we just looked at on the previous slide. We've got these same transitions, okay? What the other graph did not have is pressure. So this phase diagram is representing pressure versus temperature. So there's one important thing that is on the bottom of the slide down below the graph. As you can see, it says at the triple point, all of these phases of matter exist at the same time, okay? So at the same point, we can have solid, water or ice, we can have liquid, water, and then we can have water vapor or gas all at the same time. And that point is down below letter B. There's a dot there where it kind of splits into a Y on the graph, and that happens to be at 4.58 torr of pressure. So if you follow that dotted line across from the y-axis where it says 4.58 torr, follow that to the right, you'll run into that dot there where it kind of splits into the Y. That's our triple point that we're talking about, where you have solid, liquid, and gas all existing at the exact same time. And of course, that's at 0 degrees Celsius. So if we shift over to the graph or the phase diagram on the right-hand side of the screen, we've got the substance carbon dioxide. Okay, so carbon dioxide, notice the quadrants look slightly different. Our values for temperature and pressure are slightly different, though we are still working with atmospheres of pressure. So we have the same units of pressure and we have the same units of temperature in this graph. So we are looking at pressure and temperature still, but our quadrants look slightly different because our carbon dioxide is a solid over a slightly larger range. The gas is slightly larger, so that pushes our liquid phase in the blue there to be slightly smaller. Okay, and again, if we go back to normal atmospheric pressure being 1 atmosphere at sea level, you can notice on the carbon dioxide graph over here on the right-hand side that our value for 1 atmosphere pressure shows what we normally see for dry ice, and that is dry ice normally goes from a solid directly into a gas, which is our sublimation process that we talked about in the last lesson. So we've got this change from solid to gas by skipping the liquid state. So this is sublimation. And that happens at normal atmospheric pressure and a temperature of negative 78.5 degrees Celsius. Okay. So in order to observe our triple point for dry ice, we need to pressurize dry ice. And if you follow the graph up the y-axis, you will see that the pressure where our triple point comes across and meets the dot with letter X there in the middle, splitting again into kind of a Y type shape. Our pressure is 5.11 atm. And 5.11 atm is 5 times normal atmospheric pressure. So we need to increase the pressure surrounding this dry ice by 5 times to see the solid, the liquid, and the gaseous dry ice. So believe it or not, you can do that. And I'll see if I can include a clip in today's lesson for you in Google Classroom. Okay. So if you have any questions as you're working on your assignment, definitely feel free to send me an email or message me through Remind, and I'll look forward to getting your responses to your questions on heating curves and phase diagrams as you work on these assignments. All right, good luck, and I'll talk to you soon. Have a great day.